Warning, the video you're about to watch contains mathematics at the level of integral calculus, also known as Calc 2. All material has an assumed prerequisite of differential calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is usually meant for the end of a Calculus 2 course. However, in my Calc 2, we cover sequences and series in the middle of the course. And so this is still considered the end stopping point, I guess you could say, for sequences and series. And this is where you're talking about the error estimates for the Taylor and Maclaurin series. So let's dip our toes into this, as that first sentence says. Now, it's very high level content. It usually is reserved for numerical analysis and upper division. However, it's good to have this discussion now. So given a finite Taylor series expansion, that means given that you have worked out maybe the third degree Taylor polynomial for some given function. We know that this third degree Taylor polynomial expansion is not equal to the function, unless the function was a third degree polynomial, by the way. But for the most part, this third degree Taylor polynomial expansion is just a poor approximation to the original function. So there's some level of error associated with that. And we want to know, what is that error? How can we figure out how bad of an approximation that is? And by the way, since this is a polynomial, that is, it's a function of x, this approximation has a different level of error just depending on where you're looking. So let me give you a visual of this. First of all, generally speaking, your Taylor polynomial or your Taylor series expansion has a radius of convergence that is non-zero. Now, there are times when you have a radius of convergence that is equal to 0, but for right now, we're going to assume that our radius of convergence is greater than 0. And let's pretend that the function that we're trying to approximate looks something like this. Our third degree Taylor polynomial expansion, which I'm going to draw in blue here, is going to be exactly matching our regular function f of x at the center A. And it's going to be linked, actually I think blue is probably bad. Let's use red just because it's hard to see the blue in contrast here. It's going to be linked to our polynomial, to our function f for a short period of time, but not very long. So it might look something like that. That is, by the way, a third degree polynomial. You can kind of see here. And so you notice that there is definitely error between the true function in green and our Taylor polynomial expansion in red, our third degree Taylor polynomial that we're subbing in instead of working with the original function. But that level of error just depends on where you're looking. So for example, if I'm looking at, now I'm going to go ahead and use blue. If I'm looking at this x value right here, which I'll call x sub 1, well, the original function's value at x sub 1 is whatever that y value is. However, our approximation is way up here. This right here is our error, how far off we are from the true value of the function. So you can see that error can be pretty wild if you're far away from the center. However, the closer that you get to your center, the less error you're going to have typically. So for example, if you took a look at x sub 2 right here, and you were to look at the true function's value at x sub 2, it is almost identical to our Taylor polynomial expansion at x sub 2. So the error is very minimal. So when I talk about what is the error in our Taylor polynomial expansion, or in this case, our third degree Taylor polynomial expansion, I'm really mean on a given interval, what's the maximal error that you can expect? And that given interval is generally defined by an inequality that looks like this. The difference between x and your center is less than d. Now, even though the radius of convergence might be, let's say 10, let's just pretend as though that's the radius of convergence, you might only want to consider a smaller interval, let's say a radius of 1. So if this center, let's pretend the center was at x equals 1, and your radius of convergence was 10, that is, you are guaranteed, if you were to sum up the series forever and ever and ever, that you would get convergence from, and I'm not going to include the endpoint here, so I'm just going to say possibly from 1 minus 10, which is a negative 9, all the way to 1 plus 10, which is a positive 11. So you might get convergence on the interval negative 9 to 11, but that's only if you had added up your series forever and ever and ever. But if you only add up the first 3 terms, or in this case, technically the first 4 terms of your series, then if you want a minimal amount of error, you'll want to tighten up that interval that's centered at x equals 1 here. So you might want to consider only an interval from, let's say, 0 to 2 or something like that. And you can kind of, if you're only considering x values to plug into your polynomial that are within that interval, then you can restrict the error a little bit more. So the idea here is, if you're not really concerned about x values beyond maybe 1 unit away from the center, then maybe you should restrict artificially the interval you're considering just to be within that radius of within that radius of the center, 1 unit away. Even though your radius of convergence might be larger, it just helps by saying, listen, I only am really concerned about x values between 0 and 2 instead of between negative 9 and positive 11. There's still a varying amount of error, even on that small interval. The error just depends upon what x value you were looking at. If you're looking at the center, there's 0 error. However, as you move away from the center, the error does tend to grow. And that gets us back to this statement right here. How can we estimate that error? And there are 3 basic ways of doing this. The first is really not a way that you're going to do this unless you're in possibly a numerical analysis course in upper division, when you're first really learning the big theory behind the scenes. You use some type of graphing technology. You would graph the given function and you graph your Taylor polynomial expansion on the given interval, and then you would compare the graphs, kind of like what I did here, where I wrote down what that error is right there. But to be honest with you, when I was a student, I absolutely hated that approach, because that then means that we know the function and that we're doing the extra work of taking the difference between the function and our approximation to find out what the error is in our approximation of our function. The reality is that often you're not even handed the function, so how can you possibly even figure out the error using a graphing device and graphing the original function? If you don't actually have that function, there's just no way to do that. So that first method is a very, very poor method. Now, the second method is actually pretty powerful. Use the remainder estimate for the alternating series. This only holds if the Taylor series expansion for your function is an alternating series. So if the series is alternating and the successive terms are decreasing, therefore it converges, then you can use the remainder estimate. And the remainder estimate for alternating series is really very easy. You don't even need to know what your original function is. All you need to know is, what's the next term in line? If I only added up the first 3 terms, then the maximal value for the remainder of all the terms left in my series will be less than or equal to the next term in the non-alternating part of my series. So that's a really, really great way of finding the error, or an estimate for the bound of the error. Again, everything I'm talking about here, these are not actual errors. They're what's the worst case scenario? What's the worst possible condition that could occur here? What's the worst possible case that our error could ever be? Will your error actually become that? Possibly. but probably not. But what happens if your series is not alternating? So that's kind of, in my opinion, the worst case scenario. If the series that you're dealing with is a non-alternating series, for example, e to the x is not alternating as a power series expansion, then you have to use Taylor's inequality theorem. And this is the one that I did as an aside for my students because it's a very, I think, I don't think it's a tough theorem, but I just think it's really delving into upper division mathematics. And when you're learning Calc 2, you really want to avoid that excessive complication if you can. But here it is. If you do not have an alternating series for your power series expansion, then you take your function and you take its n plus first derivative. So remember, I'm using a third degree Taylor polynomial expansion here, so to outline this process. So that means that I would look at the fourth derivative of my function, and as long as the fourth derivative of the function is bounded by some number, and when I say bounded by some number, I really mean on this little sub-interval that you're considering. And so that's what we say up here is on that little sub-interval that you're considering. So if you're not interested in x values within your radius of convergence, like all the way from one edge to the other edge, but instead a subset of that radius of convergence, you can actually get a tighter bound on that fourth derivative. But once you find a bound for that fourth derivative, then your remainder or error, again, it's the same error here, this guy right here, is going to be bounded by that bound on your fourth derivative or your n plus first derivative divided by n plus 1 factorial times the distance between any x value in that interval minus the center raised to the n plus first power. And of course, you can find out how large that is, but you want this to be as small as possible. All right, so this ends this video, and we're gonna go ahead and clip it here so that in the next video, we can start into using each of these techniques. I'll see you there.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at ease. Says, listen close, don't talk too much that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.